Hello, welcome to Understanding Power Electronics. In this series of videos, we are looking at various aspects of power electronics. The videos are at a fairly fundamental level, so they are relatively easy to understand, I hope. Following the videos on introducing power electronics, we are going to look at some power converters and their operation. The first set of power converters that we are going to look at is DC to DC power converters. That means the input is DC and the output is also DC. There are other types of converters, AC to DC converters. For example, DC to AC inverters, DC to AC converters are called inverters. I feel it's relatively easy to start off with DC to DC power converters. The additional wrinkle due to AC operation does not exist in these converters. So let us start with DC to DC power converters. In DC to DC power converters, a buck converter or step-down converter may be considered the basic converter. It is relatively easy to understand. Let's start with that converter. We are going to have a few videos all on buck DC to DC converter. If you go through these videos, you will get a fair understanding of what buck converter is and what are its characteristics, how to design it, at least at a simple level. So with that in mind, let's get started. As I mentioned, DC to DC converters are widely used in industrial, consumer, and other applications. For example, a PC, a laptop, a phone charger, they will all be using DC to DC power converters in them. A solar PV inverter will usually consist of a few converters put together, and one of these can be a DC to DC power converter to take DC power from the solar panel and then boost up the voltage while also making sure that the solar panel operates at its optimum point. So there is a variety of use for DC to DC power converters. From these DC to DC power converters, we are going to be looking at in this video and in the subsequent videos a particular converter called a buck DC to DC converter or a step down DC to DC converter. So let's now take a look at how we can classify DC to DC power converters in a very simple manner and where the buck converter that we are going to study, where it fits in. So DC to DC power converters can be classified broadly into two types: switching type or linear type. Switching type use power semiconductor switches, power switches to turn on and off. So switching type or the power electronic type. Linear type uses linear electronics. It tends to have greater power loss. So linear type is not normally used. It has limitations of efficiency, and it can only step down, it cannot step up the voltage, and so on. But nevertheless, there are niche applications. For example, when you want to amplify a very low value signal in an instrumentation amplifier, for example, then the power supply needed for that should be noise free, and a switching type may not be suitable, and a linear type of power supply may be preferred in such cases. We can classify the switching type power converter into two parts again. One is non-isolated, the other is isolated. Here isolation refers to transformer isolation. So without transformer, with transformer. Obviously the converters without transformer in them are the simpler converters. Transformer may be used for galvanic isolation, safety purposes or other purposes, or for stepping up or stepping down the voltage level or current levels. So transformer isolated converters are also quite popular. We are now looking at non-isolated or converters without transformer isolation. The non-isolated converters can again be classified into two parts. One is what you can call as basic converters. The remaining can be called as advanced, but we are just calling it as others. Converters like SEPIC converter, zeta converter, or the LLC resonant converter used in some cases, they will all fall under this others category. Basic converters are those that are fundamental to power electronics. We can view many of the other converters as having been derived from the basic converters. So, basic converters, there are four. One is the step-down converter, which we are going to study in this video and in a few subsequent videos. Step-down means the voltage is reduced, the output voltage is lower than the input voltage. The alternate name is buck. Buck means to oppose. I'm not sure of the origin, but somehow the term buck converter has been taken to mean step-down converter also. Then, of course, step-up converter, that's boost. The name is more obvious there. Step-up converter, where the output voltage is higher than the input voltage. Then you can have a converter which is buck boost. That means it can step it down, it can step it up. The output voltage can be lower than the input voltage, the output voltage can be higher than the input voltage. That is a buck boost converter. The last one you can guess is a boost buck converter. The boost buck converter is called a Chook converter, named after the inventor. So these four converters may be considered as basic DC-DC converters. One can also consider buck and boost only as basic converters, that you can somehow derive buck boost and Chook from those two converters. It's also possible to view only the step-down converter as a basic converter and try to derive the other three converters from them. It's a matter of how these converters are topologically or structure-wise related. So as I mentioned, in this series of videos, we'll be going through buck converter and its operation. The first video you can notice is buck DC-DC converter CCM part 1. The title looks a bit daunting. Let me break it down for you. The buck converter has two modes of operation or two regions of operation. One is CCM, Continuous Conduction Mode. Another is DCM, Discontinuous Conduction Mode. The properties of the buck converter are different in these two regions of operation, so a designer must know both. So a note on the videos. So this video is CCM part 1. It deals with the basic operation, CCM operation. But CCM part 2 deals with the detailed waveforms under CCM. CCM part 1 also will deal with some of the waveforms. CCM part 2 will deal with it more completely. Then we have a few videos on DCM, part 1, part 2, maybe more. These deal with DCM operation as well as DCM and CCM put together, the overall operation. Now let's move on to what a buck converter is and what is its basic operation. Now we will understand the basic operation of the buck converter under continuous conduction mode. Right now we will dive into it, go through the operation, and then I will explain what continuous conduction mode is a little while later. This shows a buck converter. It's a very simple circuit. It has got a switch and a diode. An inductor and a capacitor acts as a filter. Vin is the input voltage, DC input voltage, and load is something that is connected to the converter, and the circuit develops a voltage V0, which is fed to the load. In doing this analysis, we make a few assumptions. The first one is that the components are ideal lossless. The inductor and the capacitor do not have any parasitic elements associated with them. The capacitor, for example, has no resistance associated with it or inductor associated with it. So in particular, the switch and the diode are treated to be ideal. There is a video in this series on ideal switch versus practical switch. You may wish to go through that. This assumption makes the analysis understanding easier. The next assumption we make is the circuit is operating under steady state. It's not undergoing a transient. The output voltage is not building up or going down. It is steady, maintained cycle after cycle. The average values are all constant. Average voltage is constant. The average current is constant. Here we assume that the circuit has already reached the steady state and we directly jump into the operation and analyze the circuit. The last assumption that we make is that this capacitor C is quite large. Capacitor C is a filter capacitor. It maintains the output voltage nearly constant. The output voltage V0 is almost pure DC. After all, the intent of the circuit is to obtain a good DC voltage, so we assume that the output voltage is a good DC voltage. We will verify later how much the output voltage deviates from a constant value. In order to understand the basic operation of the converter, we will plot some waveforms. In particular, we will plot three waveforms. The first waveform is the voltage at node A, VA. This is the common node, and the voltage VA refers to the voltage between A and this point. It is the cathode to anode voltage of the diode. The other two waveforms we will plot are the inductor voltage and current. In operating the converter, the switch is turned on for a particular interval T on and then it is turned off for the interval T off. T on plus T off forms one cycle of the waveform. We assume that the frequency of operation is constant. There are operating methods in which the frequency may be varied. For our understanding here, we treat the frequency as being constant. That means Ts is constant. And the quantity T on by Ts is D. That is the duty cycle. So T off by Ts will be 1 minus D. Notice that D cannot be less than 0. That means T on cannot be less than 0. T on cannot be more than Ts. That means duty cycle cannot be more than 1. So the range of duty cycle is between 0 and 1. Next, let's plot the waveforms. Please note that we are assuming that the circuit has reached steady state. That means V0 has reached some value. We don't know what the value is as yet. We don't know whether it is less than Vin, more than Vin, or even negative. We will see what it is a little while later. Now, the switch S is turned on for the duration T on. When switch S is turned on, a current starts to flow in the circuit. The inductor has already some current because it has been operating. The circuit has been operating under steady state, so inductor has some current. When the switch is turned on, a current flows as shown in the circuit. D is switched off because the cathode of the diode is connected to the positive of the power supply. The anode of the diode is connected to the negative of the power supply, so the diode is switched off. VA will be equal to Vin during this interval because we are assuming an ideal switch. So that is VA in this interval is Vin. If you consider the inductor voltage is VL. The plus terminal here is connected to VA. The minus terminal is connected to V0 always. So VL will be Vin minus V0. Let me first draw V0, arbitrarily some value V0. So VL will be Vin minus V0. We can plot that. So far we have not made any assumption about what the value of V0 is. Now, this V in minus V naught is applied to the inductor. We know the inductor equation VL equals L DIL by dt. So I can find the value of DIL by dt, which is the current slope, that equals VL by L. During this interval, VL will be V in minus V naught. So DIL by dt during this interval is V in minus V naught by L. V in minus V naught is a constant value. So during this interval, the inductor voltage does not change. It is input voltage minus output voltage. We assume that the capacitor is so large that the capacitor voltage is constant. V in minus V naught is a constant value. So the slope V in minus V naught by L is a constant value. So the inductor current starts from some value I1, increases at a constant rate of V in minus V naught by L, and reaches some other value I2. So this is the inductor waveform during the interval T on. Now we switch off the switch. So we are trying to interrupt the inductor current. So the inductor current starts to fall. When it starts to fall, DIL by dt is negative. So VL will be negative. So that negative voltage, that means the right hand side here will be positive and the left hand side here will be negative. So that voltage will overcome V0, output voltage V0, and forward bias this diode. So the inductor current finds a path to continue via the diode. Once the diode conducts, the voltage across the inductor is fixed at minus V0. We say that the inductor voltage is clamped to minus V0 by the diode conduction. We are considering the T off interval. T off is 1 minus dTs, and during this interval the inductor voltage is minus V0. So DIL by dt is minus V0 by L. Again, it's a constant slope, but this time a negative slope. So the inductor current falls from I2 down. The slope is minus V0 by L. And then because we are under steady state, the current has to come back to I1. That is the main thing. It comes back to I1 because we are under steady state. We are assuming operation under steady state. Now a word about this diode. During the off interval, the inductor is not connected to the power supply. Instead, it is connected via the load and the diode back to itself. So the current is sustained without a power supply being present. This action is called as a freewheeling action. It's as if a gear wheel is connected to the motor and the motor is disconnected, but the gear wheel continues to turn. So the power supply is disconnected, but the current continues to flow in the inductor. That's the idea. This is the freewheeling action, and this diode is called as the freewheel diode, and this interval T off is called as the freewheeling interval. Next, we again switch on the switch. When the switch is on, the diode switches off. The current flows in the main loop. VA is equal to V in again. VL is equal to V in minus V0 again. And the inductor current increases at the rate V in minus V0 by L. And next, when we switch off the switch, the inductor current freewheels through the diode. VA voltage becomes 0. VL becomes minus V0, and the inductor current falls at the rate minus V0 by L. This process repeats cycle after cycle. So cycle after cycle, the waveforms are identical and the pattern repeats. We are switching at a constant frequency. You can get an idea of the basic operation. We still have not seen what will be the V0 voltage. For example, how is the inductor current related to the load current? These aspects we'll now see one by one. Next, we will see what is the value of the output voltage. How is the output voltage related to the input voltage? Is the output voltage related to the load current? That's what we are going to see now. The inductor current is under steady state. Starting from some value I1, it returns to that same value I1 at the end of the cycle. For this to be true, the inductor must be under volt-second balance. What that means is integral 0 to Ts VL dt should be 0. There is a video on this which delves into this in greater detail in the introduction series of videos. You may want to take a look at that. For now, we will assume that we know this. That means the integral of this inductor voltage waveform under steady state over a period must be 0. Then only the current will return to I1. So that means the area under the VL curve over a cycle must be 0. A plus plus A minus must be 0. So the positive area must cancel out the negative area. During the positive area, the current will go up. During the negative area, the current will come down. And in order for it to come down to the same value, positive area and the negative area must cancel out. A plus is V in minus V naught times T on. A minus is minus V naught times T off. So these two should add up to 0. We can write it down. V in minus V naught times T on plus minus V naught times T off equals 0. I can solve for V naught by V in from this. You can work it out on a piece of paper. And if you do that, you will find that V naught by V in is T on by T on plus T off. T on plus T off is one period, so that is T on by Ts, which is of course the duty cycle. So the output voltage ratio V naught by V in is duty cycle, and D is between 0 and 1. At this point, you can note, since A plus plus A minus must be 0, the positive area equals in magnitude to the negative area. They have to cancel out. So V naught cannot be more than V in. If V naught is more than V in, then A plus becomes negative. So there is no positive area. So the volt-second balance will not work. So V naught cannot be more than V in. Likewise, V naught cannot be less than 0. If V naught is less than 0, then minus V naught will become positive. So A minus will become positive area. So again, positive area will not cancel out the negative area. So from volt-second balance, you can see that V naught cannot be negative, V naught cannot be more than V in. Notice here that the duty cycle range is between 0 and 1. Duty cycle cannot be negative. So since the duty cycle is not negative, V naught cannot be negative. So we get the same result as we got earlier. Likewise, duty cycle has to be less than 1. V naught will have to be less than V in. So this pretty much defines the range of V naught. So V naught ranges from 0 to V in. It is a step down converter. It can give an output voltage from 0 volts to input voltage. In practice, we can go down to almost 0 volts and can go up to almost the input voltage. Notice that by varying the duty cycle here, output voltage varies. So we have got a degree of control. So this is the turn on interval T on. This is the turn off interval. By adjusting the turn on, turn off ratios, we can vary the output voltage. Next, we will see an alternate way of deriving the same equation. Look at this loop. This voltage is VA, this is VL, this is V naught. V naught is a DC voltage. VA, VL and V naught, if you take care of the signs properly, they should add up to 0. So VA minus VL minus V naught equals 0. VA is a function of time, that's why I have used a lowercase v. Likewise, VL is a function of time, I have used a lowercase v. V naught is constant. We are interested in finding the value of V naught. The VA waveform is a periodic waveform. VL waveform is a periodic waveform. So this periodic waveform will have an average value and the harmonic components. The Kirchhoff's voltage law will be valid for each one of these components. Let us apply the KVL to the average values. So VA average minus VL average minus V0 equals 0. VL average is the DC voltage across the inductor. If we have any DC voltage across the inductor, the DC current will keep increasing in the inductor because LdI by dt is V. So an inductor cannot have any DC voltage across it under steady state. This is another way of stating the volt-second balance. So VL average is 0. So VA average equals V0. So the average of this green waveform is V0. The average of the VA waveform V0 is given by 1 over Ts integral 0 to Ts VA dt. So integrate the waveform over a period and then divide by the period. And integrating the waveform over a period is the same as taking the area of the waveform. The waveform here is 0, so it is V in times T on. The output voltage V0 will be 1 over Ts V in times T on. T on by Ts is duty cycle, so once again V0 equals dV in. So we get the same result as you would expect. Again, the story is by changing the duty cycle, we are able to control the output voltage. Now we will see a bit more about the output voltage versus duty cycle. This shows the buck converter again. The switch is typically a power semiconductor device. Typically it has a gate terminal to control the switch on and off. So here I have shown it as C for control. By giving an electronic signal, we can turn it on and off at any point in time. We also know that the output voltage is the average of the VA voltage. So let's plot the VA voltage. Assume that the duty cycle is 0.1. That means for 10% of the period, the switch will be turned on, and for the remaining period, the switch will be turned off and the diode will be conducting. So this shows the VA waveform. This is the T on interval, and during this interval, VA of course equals V in. The rest of the interval, it is 0. VA is a pulse voltage. The pulse interval is controlled by the duty cycle. The average of this voltage is the output voltage, and here the average is going to be pretty small because the pulse is narrow. The average V0 is dV in, which is 0.1 V in. The output voltage is 10% of the input voltage. Now let's increase the duty cycle to 0.4. The width of the pulse has increased to 0.4 of the period. Now we can see that the average of this waveform is going to be higher, and it is 0.4 V in. So the output voltage increases from 10% of V in to 40% of V in. Now let us change the duty cycle to 0.7. Width of the VA pulse increases to 70% of the period, and the output voltage increases to 70% of the input voltage. Likewise, if we increase the D to 0.9, the width of the pulse will go to 90% of the period, and the output voltage increases to 90% of the input voltage. We can choose any duty cycle we want between 0 and 1. Typically, we cannot go too close to 0 or too close to 1, but otherwise we have pretty much the whole range. We are varying the width of the pulse VA in order to control the output voltage. For obvious reasons, this technique is known as pulse width modulation. Most power electronic schemes will be using pulse width modulation methods one way or the other to control the desired quantities. Now let us plot V0 by V in ratio with respect to D. That's a simple straight line. And as we increase D, V0 by V in increases it linearly. And when D equals 1, the V0 by V in maximum that you can get is 1. Thus, by varying D, we are changing the gain of the converter. Because we have assumed all components to be ideal, the switch, the diode, the inductor, capacitor, etc., the efficiency of the converter is going to be 100%, theoretically at least. Practically it will not be, but theoretically it's going to be 100%. By controlling the switch operation through some electronic signals, we are able to vary the output V0. So I'm showing it in this diagram as a control here, which is some electronic circuits producing pulses for controlling the gate of the power device. Thus, we can see in a very simple manner, power electronics provides the interface between the world of electrical power and the microelectronics world. That is the main business of power electronics. That's what power electronics does. Next, we will see briefly what is continuous conduction mode and what is discontinuous conduction mode. A buck converter and many converters, in fact, have regions of operation. This buck converter has two regions of operation or two modes of operation. The first mode is the continuous conduction mode that we are studying now. Here, when the switch is on, the inductor current starts from I1, reaches a value of I2, and when the switch is off, the current freewheels through the diode and the current returns to I1. The current I1 does not come to zero and stay there. If it does, then it will be the other mode of operation. Here you can see that in each period of switching, there are two main intervals. One T on when the switch is on, one T off when the switch is off and the diode is conducting. T on, switch is on, T off, diode is on. The other mode of operation is discontinuous conduction mode, or DCM for short. In this mode of operation, the inductor current starts from zero. It will become clear why it has to start from zero. It starts from zero. It goes to the peak when the switch is on, and then when the switch is off, the current freewheels, but the current does not freewheel through the whole interval T off. The current quickly falls to zero, and once the current falls to zero, it stays there. The diode is also off. Here in one switching period, you have three intervals of operation. One when the switch is on, second when the switch is off and the diode is conducting, third when the switch is off and the diode also is not conducting. So the operation of the converter, it turns out, as you can expect, is different in these two regions. A designer should be aware of both the regions and design accordingly. Now we will continue with our study of the continuous conduction mode operation of the buck DC-DC converter. Next, we will determine the ripple inductor current. This is an important parameter in the design of the inductor and also the design of the converter itself. We are plotting the inductor current waveform here. The current starts from I1, goes to I2 when the switch is on, and then when the switch is off, falls to I1 back again. During T on interval, the voltage across the inductance is Vin minus V0, and the slope of the inductor current is Vin minus V0 by L. We wish to find out delta IL. Delta IL is the peak-to-peak inductor current ripple. To find that is fairly straightforward. Take the slope Vin minus V0 by L, multiply that by the interval T on, and we will get delta IL. So that's it, we are done. We can express this in a slightly different way. We know T on by Ts is the duty cycle D, and V0 by Vin also equals duty cycle D under continuous conduction mode. V0 equals dVin and T on equals dTs. Substituting them here, we get delta IL equals Vin minus dVin by L times dTs. I can take the common Vin out. So delta IL is V in Ts by L d times 1 minus d. In many applications, we would like to keep the output voltage V0 constant by varying the duty cycle d. So in such designs, we will already know the V0, so it makes sense to express this equation in terms of V0 in those cases. So V in is V0 by D, and then substituting that here, D and D will cancel. We will get delta IL equals V0 Ts by L 1 minus D. Either of these equations will give you the delta IL value. Next, we will see the relationship between inductor current, capacitor current, and the load current. Notice one thing. If you look at the output voltage V0, that equals dV in. The output voltage depends on the input voltage and the duty cycle. As long as the operation is in continuous conduction mode, the output voltage does not depend on the load, at least ideally. In practice, the output voltage will vary slightly with the load. The input voltage and the duty cycle determine the load voltage. The load current is determined by the load and the output voltage. That is something to keep in mind. Here we are interested in finding the relationship between load current, capacitor current, and the inductor current. Let's plot the inductor current waveform. This is delta IL. This is the slope during on interval V in minus V0 by L. Now this current can be split into two parts. There is a DC part or the average current part, and the remaining or the ripple part or the AC part. I can write IL equals IL average plus IL AC. IL average is the DC part and IL AC is the ripple part. The brown line here, this is the DC part of the inductor current waveform, and this is the remaining AC part. Now if you consider the DC part of the inductor current, that DC part cannot flow through the capacitor. As you know, if the capacitor absorbs DC current, that means the average voltage or the DC voltage will be changing. So it is not under steady state. Charge balance in each cycle has to be maintained. The DC current going into the capacitor under steady state has to be zero. That means the inductor average current or the DC current of the inductor flows through the load. That is straightforward. Now what about the AC part of the inductor current? In order to understand this, let us focus on the output side of this circuit. The capacitor is parallel to the load. To understand it in a simple manner, let's consider a resistive load or the load as being a resistor. Now, consider the fundamental of the current, IL current. IL AC current has a triangular wave shape. It has got a fundamental component and harmonic components. Consider only the fundamental just to keep things simple. Fundamental frequency is of course the switching frequency, Fs. Omega s, the angular frequency in radians per second, is 2 pi Fs equals 2 pi by Ts. I can draw the output side as an AC circuit. A sinusoidal component of the current flowing into it at the fundamental frequency. You have a capacitor, you have a load resistor. This capacitor is chosen to be large. The capacitor impedance is of course 1 by j omega sc. And since this capacitor is chosen to be large, it is safe to assume 1 by j omega sc is much less than R. So there is a parallel circuit here. This impedance is much lower than the load. By applying Kirchhoff's current law and current division, we know that most of the current will flow through the capacitor. So most of the ripple current is going to flow through the capacitor. Very little of the ripple current will flow into the load. So here IC bar With this assumption, it's a sinusoidal current. IC bar is almost equal to IL bar, the sinusoidal ripple current in the inductor, and I naught bar, the ripple current in the load resistor, will be 0. So you can see that the inductor ripple current, most of it is going to flow through the capacitor and very little of it is going to flow through the load. For the harmonics of the ripple current, the capacitor will provide even a lower impedance path. So the filter capacitor C provides a low impedance path for the ripple current ILAC. So what is the story here? The story is the inductor current can be split into two parts, the DC part and the AC part. All of the DC part goes into the load. Most of the AC part, almost all of the AC part goes into the capacitor. There is a very neat split there. So IL average equals I naught and IL AC equals IC. I naught is determined by the load and the average inductor current is determined by I naught. And the ripple inductor current is determined by the inductor, the input voltage, and the duty cycle, etc., as we saw before. To end this video, we'll work out a problem. Let V in be 25 volts, D is given 0.4, Fs is 100 kilohertz, and C is assumed to be large, and the output power is given as 60 watts. The load is drawing 60 watts of output power. The first part of the problem is determine value of L such that the peak-to-peak ripple inductor current is 40% of load current. This is one way a designer might say, I'm going to choose my inductor by placing a limit on the ripple current value. So Ts, the switching period, is 1 over Fs is 10 microseconds. 1 over 100 kilohertz, it is 10 microseconds. The duty cycle is 0.4. So T on is 4 microsecond and T off is 6 microsecond. V naught is dV in, D is 0.4, V in is 25 volts, so V naught is 10 volts. I naught, the output current, as I said, I naught depends on the load and the load power is given here. We already know the voltage, so 60 watts by 10 volts, that will be 6 amperes. That will be the load current. Delta IL is 40% of 6 amperes, that is 2.4 amperes. One little point here, I've drawn the IL waveform here. The average of the IL waveform, that is I naught, that is 6 amperes. And the peak-to-peak ripple current is I2 minus I1. So I naught minus I1 will be half of that. So this is delta IL by 2. If delta IL by 2 is less than I naught, then I1 is not going to touch 0. So the operation is in continuous conduction mode. Delta IL by 2 is of course 1.2 amperes. It is less than 6 amperes. So we are in CCM. Just to ensure that we are in CCM and not somewhere else. Now delta IL 2.4 amperes is V in Ts by L, D times 1 minus D. V in is 25 volts, Ts is 10 microseconds, L is to be determined, D is 0.4. So you can plug in all the values and compute L. If you do that, you will get 25 microhenry. So if you use 25 microhenry in this design, under this operating condition, the ripple current will be 40%. If you want to make sure that the ripple current does not exceed 40%, then you might want to give a safety margin. The inductance can be made a little higher, maybe 25 microhenry plus 10%, for example. Lastly, we will draw some waveforms, plot VL, IL, I naught, and IC. When you plot these waveforms, plot them one below the other so that the time points are synchronized, and also mark some critical voltage and current values. This is the circuit diagram. These are the specifications: Ts, T on, T off, V in, V naught, I naught, and delta IL. We can easily plot the waveforms following our discussion so far. This is the VL waveform. During the T-on interval, the VL voltage is Vin minus V0, which is 25 minus 10, which is 15 volts. And during the T-off interval, VL voltage will be minus V0, and minus V0 means minus 10 volts. Next, we will plot the I0 waveform. I0 waveform, this is the I0 waveform. I0 equals 6 amperes. Following this, we can plot the IL waveform. This is the inductor current waveform. The average of the inductor current waveform, or the DC value, is I0. So I0 is 6 amperes. And delta IL is 2.4 amperes. So IL swings by delta IL by 2, that is 1.2 amperes in either direction. So I1 will be I0 minus delta IL by 2, that is 6 minus 1.2, which is 4.8 amperes. I2 will be I0 plus delta IL by 2, which is 7.2 amperes. So you can plot the IL waveform knowing the I0 waveform and the ripple. Next, we can plot the IC waveform. The ripple part of the inductor current, or the AC part of the inductor current, is the capacitor current. So it is simply the inductor current pushed down by I0 value 6 amperes. So we show it here. The peak-to-peak ripple capacitor current is the same as the peak-to-peak ripple inductor current, which is 2.4 amperes. So delta IC is the same as delta IL, which is 2.4 amperes. Delta IC by 2 is 1.2 amperes. The capacitor current swings from I1C to I2C. I1C is minus 1.2 amperes. I2C will be plus 1.2 amperes. So there is an AC ripple current at the switching frequency of peak-to-peak value 2.4 amperes flowing into the capacitor. It is important that the capacitor be able to withstand this current without getting overheated. With this, we have come to the end of this video. In this video, we saw the basic operation of a buck DC-DC converter, its voltage gain and inductor current ripple, capacitor current ripple, and the relationship between the inductor current, capacitor current, and the output current. We will continue our discussion of the DC to DC buck converter in part 2, CCM part 2 video. Thank you. In case you find this video and this series of video interesting and useful to you, please consider subscribing to this channel and clicking the like button. Thank you.